Hello, everybody, and welcome to week 6 of Math 4400. So this week we're going to talk about cryptography. I'm just going to do basically a taste of the subject of cryptography. And it's a nice change of pace from what we've been doing so far. I mean, you guys have been sort of heroic with your willingness to do computations and modular arithmetic in various settings and to learn about these computations without having a clear picture maybe of why we're doing this and what you can use this for, besides maybe a few fun examples like computing digits of numbers. So today, or this week rather, we have a little bit of a payoff of that, and we get to see a little bit how some of these ideas show up in cryptography. So today, I'm going to talk about 2 topics in that direction. These are shift ciphers and the Diffie-Hellman key exchange. Okay, so what is a shift cipher? Well, what is cryptography first? Cryptography is in the study of how you can send secret messages to other people. Oftentimes we want to communicate with other people, and oftentimes we only want to communicate with a single person or 2 people or a group of people. We don't want everyone reading our messages. And so cryptography gives us ways to do that. One of the most elementary constructions in cryptography, going back hundreds and hundreds of years, maybe thousands of years, is the idea of a shift cipher. Oops, I think cipher is spelled with an I, not a. Actually, I don't know if cipher is spelled with an I or a Y, but I think I've spelled it elsewhere with an I. So let me do it with an I here. And cipher is sort of synonymous with code or encryption or so on. But okay. Okay, so the shift cipher. Well, I take a message like hello, and then I take a number. Here I'm going to take the number 3. And then I take each letter in my message and I shift it by 3 letters. So H, well, I go to the right 3 letters, so just in the alphabet. So I go to H, I, J, K, is what my H becomes. E becomes, well, F, G, H. L becomes M, N, O. And M, N, O again for this L, and then O becomes P, Q, R. So I take each letter and I shift it to the right by 3. So you can see this illustrated in the diagram. If I get to the end of the alphabet, I just wrap around. So like Z goes to C, for example. Okay, and so, well, if I have a buddy and so we want to be able to send each other secret messages, well, maybe we're talking at lunch one time and we say, okay, next time you send me a message, just use a shift cipher. We're going to shift by 3. Then we both know that when I send him KHOOR, to read that, he's got to undo the shift. So he's got to shift it back by 3, each letter, to get hello. And that's sort of a rudimentary way I can send something that looks like nonsense, but my friend can still read it because we've sort of pre-agreed that we're going to use this 3 shift as our cipher. Okay, so so here to encode, you just shift each letter by 3. And to decode, you shift each letter by -3. So you just shift to the left, you undo the shift. And just to be completely explicit, let me do an example uncoding. So say I send my friend hello, and he sends me back the letters CHEUD. I just have to go back to the left in the alphabet 3 letters. So C, I go B, A, then Z. H, I go G, F, then E. E, I go D, C, B. U, I go T, S, and R. And D, I go C, B, and A. Okay, so my friend is not much of a conversationalist. I told him hello, and he told me zebra. But hey, he sent me the message, so that's good. Okay, so everything we do, we're actually going to build on this simple idea. Of course, there's nothing special about shifting by 3 letters. I could shift by sort of any integer number of letters in the alphabet. And if I shift by 26 letters, I'll just end up back where I started from. So really, the integer k I shift by only matters up to sort of modulo 26. I have at least 26 different choices for how I can shift. Of course, if I shift by 0, then I'm just sending my message, and that's not a very effective cipher. And in general, actually, if I use one of these shift ciphers and I sort of shift all my letters by 7, well, if someone intercepts that message, so say me and my buddy have an enemy, that enemy intercepts our message, well, they might not know the shift, but if they just know that we're using a shift cipher, then they won't have a problem decoding it, because, well, there are only 26 possibilities. It won't take that long for them to just try all 26 options and see which one sort of produces an intelligent English message. I mean, that's one of the problems with the English language, is that it's very structured. Well, it's one of the good things and one of the bad things. But the English language is very structured. I mean, if you shift the letters of a sentence, it becomes nonsense. And sort of, if you just write down like one of these shifts, like there's always only going to be just one shift that isn't nonsense. Like, it's not like because you would have to try very, very hard to write down a message that's such that when you shifted it by like 7 letters, that what you got was not nonsense. I mean, it would be a very exceptional message in that way. So, I mean, somehow if our enemy has a little bit of patience, they can just try a few shifts until they find one that like turns it into intelligible English. And they don't even need to do it on the whole message. Like, they could pick sort of like 10 or 15 or 20 letters in the message and just do the shift on those 20 letters. And that will actually, they'll be able to see like when those 20 letters like turn into sort of some intelligible English, maybe with a broken word at the start or end, but they definitely won't have to do it to the whole message to figure out what the shift is. Okay, so that's not so good. If I want to use this to actually keep my communication secret. So one way you can handle this is you can just change the shift very often. So say I wanted to send the message 10 monkeys to my friend, and sort of yes-anding his message of zebra. So if I want to take these 10 monkeys, what I could do is I could take the first 4 letters and shift those by sort of one number K1, then the next 4 letters and shift those by K2, and then I have 2 letters left, and I'll just shift those by a third different shift. So I sort of pick 3 different shifts. K1, K2, K3. And now it's a lot harder for someone who intercepts it to just try all the shifts and see which one makes sense. I mean, if I just have 4 letters in the middle, like tenma, that's sort of a nonsense string of letters. So, and they can't tell, they won't be able to tell like when they got the right shift of this. And like anke, like that's a nonsense string of letters. So like when they shift it, it will also be a nonsense string of letters. So somehow they're not going to be able to tell individually in each of these things by shifting it which one is right. So the only way to do it, like the only way for them to figure out what the shift is will be to try sort of all possibilities simultaneously for K1, K2, and K3 until so they put those together to see sort of what gives you intelligent English. And now there are sort of many more possibilities they have to try. They have to try 26 cubed because they have to sort of try all the possibilities for the first shift, the second shift, and the third shift. And that's, I'm assuming they know the pattern I'm shifting by. So I'm shifting every 4 letters, and then I'm changing my shift every 4 letters. There's an issue with this though, because how did me and my buddy decide how we were going to communicate in the first place? Well, we met up at lunch, and we said next time we send each other a message, we're going to shift the letters by 3. This time, like when we meet up at lunch, we have to say, okay, next time I send you a message, it's going to be sort of at most 12 letters long. I'm going to shift the first 4 letters by K1, the next 4 letters by K2, and the last 4 letters by K3. Okay, so that's a lot more information I have to transmit at lunch. And maybe we want to talk to each other. Maybe we want to send each other's messages more often than we have time to sort of talk in person at lunch. Okay, so somehow, if I want to communicate with my friend and I want to do it securely, this idea of shifting very often is good, but I really need to be able to decide what the shift is somehow with my friend without getting together to meet. And I have to be able to sort of do it in a quick way so I can change it very often. And that will sort of give me a secure way to communicate. Okay, so let's set this up in sort of the general framework. So instead of me and my buddy, when we're talking about cryptography, usually we talk about Alice and Bob. So Alice and Bob want to communicate. And okay, so they want to use this mechanism where they're going to do the shift cipher, and they're just going to change the shift very often. And Alice and Bob live far away, or maybe Alice and Bob live on opposite sides of the hallway, and they don't find time to be in the same room very often. But they want to somehow find the right shifts without anyone else finding out. Okay, and so what they don't want to do is serve Alice on her side of the hall and Bob on his side of the hall. And they don't want to have Alice shout, just shift by 17 for the next 4 letters. Because Bob will get that information. Bob will know what to do. But if there's anyone else sort of standing outside in the hallway, maybe just out of sight, so this is Eve for eavesdropper or for everyone, well, she gets the information too. So Eve also knows that they're going to shift by 17 for the next 4 letters. So, I mean, somehow if Alice sends the message by then shouting out the letters across the hallway, Eve will also be able to decode it. Okay, well, and this is sort of silly because, of course, people don't communicate by shouting across hallways, except we do because that's what you're doing when you communicate on the internet. When you send a message on the internet, you're shouting it across some giant hallway, some giant electronic hallway in which like anybody could be listening. So you should think of communicating data across the internet as shouting across a hallway. Okay, so Alice and Bob can't do this. They can't just shout out what their shift is going to be, because that breaks the security, because anyone listening will also know what their cipher is. So the idea of the Diffie-Hellman key exchange is to address this. So the Diffie-Hellman key exchange is it's a way to establish a shared secret using only public communication channels. So in this case, it's a way for Alice and Bob to shout things at each other across the hall. Each of one of those things is something someone else can listen to, but in the end, they'll have a shared secret that no one else understands, that no one else knows, even if they heard everything else. Okay, so this is, the first time you see this, is pretty mind-boggling that this is possible, that you can establish a shared secret, making communications that everyone else can hear. Well, that's the magic of mathematics. I mean, all your life, you've probably known mathematics can be hard. And now finally, we have a use for mathematics being hard. There are many different ways to do this. The Diffie-Hellman key exchange is just one way. And it uses modular arithmetic. Okay, so what's the setup? We're going to choose a prime number p. In practice, p will be a very, very big prime number. But for the examples, we'll just use small prime numbers. And then we're going to choose an element g in FP cross, so an element with a multiplicative inverse, or just a non-zero element in FP or Z mod PZ. And well, we want that to be a primitive root. So you can ignore what that is right now. I'm going to come back to that right at the end of today, and we'll talk about it more during the work session on Tuesday. But for now, you can just think you just have some arbitrary element of FP cross. So just a concrete example to keep in mind as we go through everything will be P is 29 and G is 2. So 2 thought of as an element of F29, or Z mod 29Z. Okay. So Alice and Bob want to get a shared secret. We're going to call that secret Z, and their secret will be an element of FP cross. So it'll be sort of a number between 0 and 28. And then, like, for example, once they have that shared secret, they can use that number between 0 and 28. They can use that as their shift for a shift cipher. So somehow, once you have a shared secret, then you can encode any information. But the trick is to get a shared secret in the first place. They want to produce some number Z that only they know. But to produce this number, they're going to have to communicate across this open hallway. So they can't just shout, one of them can't just pick Z and shout it across the hallway, because then everyone will know. Okay, so how are they going to do this? Well, first, Alice and Bob are each going to pick privately, so not sharing with anyone, a number. So Alice will pick the number little a, and Bob will pick the number little b. Okay, so when I say number here, I just mean an integer. So little a could be 10. And little b could be 18. And so Alice and Bob, and they should pick these at random. Okay, so good. So they have this. And then what they're going to do is Alice is going to make a computation. So Alice knows the number A, and sort of everyone knows this prime number 29, and this prime number P, and this primitive root G. So that is sort of public information. So in particular, Alice knows G, she knows P, and she knows A. So she can compute G to the A modulo P. She's going to call that X. And Bob doesn't know A, but Bob knows B. So Bob can compute Y, which is G to the B mod P. Okay. So each of these computations, like this computation uses a piece of information that only Alice knows, and this computation uses a piece of information that only Bob knows. And then once Alice has computed X, she's going to send it to Bob. And once Bob has computed Y, he's going to send it to Alice. Okay. So for example, so when we have this P equals 29, G equals 2, A equals 10, and B equals 18, then Alice computes to the 10, which is 9. And Bob computes to the 18, which is 13 modulo 29. Okay, so that means, okay, so Alice is going to send Bob 9, and Bob is going to send Alice the number 13. So after then, that the point is sort of A and B are still secret. So still only Alice knows A, and still only Bob knows B. But now Alice knows something that was produced using A, and Bob knows something that was produced using A, this X, and Alice knows something that was produced using B, this Y. Okay. And now the point is sort of they can use this information to compute the same thing, just using sort of some properties of arithmetic. So Alice, and so everyone knows X and Y because Alice and Bob sort of sent those through public channels, so anyone can know that information. So, okay, but Alice in particular knows Y, and she still knows her secret information A. So she can compute Y to the 8th power. But Y, which is what Bob computed using his secret information B, is just G to the B. And just using the laws of exponents, that's G to the B times A. I'm doing this whole computation modulo P. On the other hand, Bob can compute X to the B, because Bob knows X because everyone knows X. This went across public channels. And Bob knows B because that's his secret private number. And so he can compute X to the B, but X, this was the thing Alice sent out, and she computed as G to the A. So X to the B is G to the A to the B. And again, using just the basic properties of exponents, that's G to the A times B. Okay, and G to the A times B is the same as G to the B times A. Okay, and then I just take this modulo P. So if you work this out in this example, well, Alice takes Y, which in this case was 13, and then raises it to little a, which she had chosen to be 10. So she computes 13 to the 10. And if you work that out, you'll get 7 mod 29. And then Bob computes 9. So that's the number Alice sent out, X, to the 18th power. 18 is Bob's secret number. And he also gets 7 mod 29. Okay, so this number 7, this is their secret. This is a number that both of them were able to compute pretty easily just by sort of raising to a power. Raising to a power sort of modulo prime is a pretty easy computation, as we'll discuss in class on Tuesday. Good, but so they were each able to do a simple computation using only this information been shared publicly, plus their own piece of private information to get this number 7 that they now both know. But Alice, but Eve, or sort of anyone else listening, doesn't know this number 7 because somehow only Alice knows little a and only Bob knows little b. And if you don't know little a and you don't know little b, then X and Y don't help you compute what the shared secret is. Okay. And so because of that, like now they have the shared secret, they can safely use it as a shift cipher, for a shift cipher, at least for a little while. They could send like 4 or 5 characters, no problem. And so no one's gonna be able to crack what the shift is just based on those 4 or 5 characters. Okay, so that's the idea of the Diffie-Hellman key exchange. Let me just go through that again with a little comic strip. So here's a setup. Here's Alice. Here's Bob. And here's a big signpost out in the out in the hallway that says, today's Diffie-Hellman data, P is 29 and G is equal to 2. So everyone has access to this. Everyone can see this. Bob can see it, Alice can see it, and Eve can see it sitting out here. Okay, and so then Alice, inside her head, she picks this random number, A equals 10. And then she does the computation using the information on the sign plus her number A. So she computes 2 to the 10. So the 2 to 10 modulo 29, and she gets this little number 9, and she shouts out 9. So Bob knows the number 9 now because Alice has just shouted it out. And then Bob does the same thing. He picks a random number. He picks 18. Then he computes 2 to the 18, which is 13 mod 29. He takes that result and he shouts out 13. So now Alice also knows 13. And Eve knows both those things as well. So Eve, sitting out here in the hallway with her computer, has written down 9 and 13, and she's feeling pretty good. She's feeling like she's going to crack their code. Okay, but then what happens next? Alice does a computation. She takes this number that Bob sent her, 13, and she raises it to her secret number, 10, and she gets 7. So she says, got it. Bob does the same thing. He takes the number Alice sent her, which is not what I wrote here. Try it again. 9. So he takes the number Alice sent her, 9, and he raises that to his secret number, 18, and he gets 7. So now they both know 7. So he shouts out, got it. And Eve is left sort of sad and confused. She was expecting him to sort of maybe say something else and give away their secret, but they've already said everything they need to say. They both know 7, and there's no way for Eve to get this number 7. Okay, so just here's a little table. I just want to sort of fill in who knows what. So P and G, so this is the starting data, like 29 and 2. So a big prime number and then a primitive root. And everyone knows that. A is only known by Alice, and B is only known by Bob. Then X, well, Alice computes it, but then she sends it out, so everyone gets to know it. And then Y, same thing, Bob computes it, then she sends it out. Then he sends it out, and so everyone gets to know it. Okay, so that's the premise of everything. It's like once you send information out, everyone gets to see it. But then, once all of this is set up, only Alice can compute Z, and Bob can compute Z, but Eve doesn't have enough information to compute Z. And somehow, to compute Z, you need to know either Y and A or X and B. So you need to know Y and A, like Alice does, or you need to know X and B, like Bob does. And so they can both compute Z, but Eve doesn't have a good way to compute Z. So somehow, even though she's seen all the information that's gone across, this P and G to start out with, and this X and Y, she doesn't get this shared secret. She doesn't have a good way to get it. So yeah, so just to make that explicit, I mean, okay, to compute Z, and Alice really needs to know A or B, and she knows X or Y, so she just needs to know one of A or B. And she knows how the system works, actually. And we can assume that Alice is versed in Diffie-Hellman, or we can assume, sorry, this should say Eve. Eve is our eavesdropper. To compute Z, Eve needs to know A or B. So we can assume Eve is sort of versed in how Diffie-Hellman works. So she knows this number that Alice shouted out is G to the A. And she knows this number Bob shouted out is G to the B. And so what she needs to do is sort of compute the logarithm base G. Like, so A is the logarithm base G of X, and B is the logarithm base G of Y. I mean, so this is called the discrete logarithm problem. So it's log sort of in a finite field. So it's nothing like logarithm. I mean, somehow it looks like logarithm, like over the real numbers or complex numbers, but you don't have like this explicit formula in terms of power series or anything. So you have to be a little bit more careful to understand how to compute logarithm in this setting. So it's formally very similar, but actually computing it is very different, is the point. And it turns out there isn't a good way to compute discrete logarithms. So like in this example, one of the computations Eve could try to do is sort of try to compute log base 2 of 9. So 9 was sort of 2 to the 10, and the 10 was Alice's secret number. So that's sort of why she wants to compute that. But Eve only knows 9 and she knows 2. So she knows this is what she needs to compute, but she doesn't have a good way to do it. And that's the point. Basically, the only way she has to do it, like the only way you can attack this that sort of people know, is to just write out all of the powers of 2 sort of inside of this finite field, F29, until she hits 9. So if you just start doing that, okay, 2 to the 0, 2 to the 1, 2 to the squared, 2 to the cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th, 2 to the 10th, I got 9. Okay, so now I've computed it. So this sort of gives you that log 2 of 9 is equal to 10. So I found Alice's secret. So after she's found Alice's secret, then now she can compute y to the a and she gets c. So z was y to the a, where y was sorry, back in this example, y was 13. So Eve does have a way to break this code. Like she can do this discrete logarithm computation, but the point is it's hard. It's not so hard in this example where we're working in a field of 29 elements, but in practice, you don't work in the field of 29 elements, you work in the field with like the element, like you work in FP where P is a prime with like 50 digits. And then that's a lot of computations. I mean, because you're just going to serve, if you have 50 digits, I mean, that's like 10 to the 50 computations you have to do because you just have to compute sort of 2 to every power. Like you don't know, there's no way to sort of optimize that. You just have to sort of compute all of them in order to find, unless you get very lucky. Whereas by comparison, like Alice and Bob, and they also have to compute some powers, like that's sort of, they have to compute x, which was like 2 to the a, and then they have to compute y to the a, and so on. Like those were Alice's computation, but that's just 2 powers. Like, so the difficulty does not come from the fact that they have to compute power. Like it's not so hard actually to compute powers in FP. Like if you just have 1 or 2 of them, and that's all Alice and Bob have to do. What's difficult is to compute sort of all of the powers in FP, not because computing any individual one is hard, just because, I mean, somehow you have to compute a lot of them in general. Okay. And so that's basically where I want to stop, except I should come back to this asterisk from the very beginning about our data, which said, when I chose this number G, this should be a primitive root mod P, so in FP cross. So what does that mean? Well, it's basically because of this thing I just said. I mean, I want it to be hard to list out all of the powers of like 2 mod 29. But there are certain choices of elements in F29 cross where it's not hard to list out all the powers. For example, I don't know, it's not hard to list out all of the powers of 1. Okay, yeah, it'd sort of be bad if you chose G to be 1. So what you want then is something called a primitive root. So an element if I have a field, a finite field, then an element G inside of here is called a primitive root if I can write every element, every non-zero element as a power of G. So that sort of tells me that there are as many different powers as possible of G, so that this problem of sort of computing all of them is going to be as difficult as possible. Good, but we'll talk a lot more about that in class on Tuesday, and so I will see you there.